friends, welcome to this lecture. In this lecture we will discuss the Frobenius series solution method for second order linear differential equation, and it is we are considering this Frobenius series solution method for the case when we have a point which is a regular singular point. So how we can understand, if you look at the equation like P naught t y double dash t plus P1 t y dash t plus P2 t y equal to 0. So, this is a second order linear differential equation where P naught t, P1 t and P2 t are some continuous function in terms of t. A point t equal to t naught is said to be a singular point of this if P naught at t naught is equal to 0. And so, when we have a singular point, then we say that t equal to t naught is a singular point of this ordinary differential equation. And if in addition to this, if t minus t naught P1 t divided by P naught t and t minus t naught square P1 t P2 t divided by P naught t, if these two functions are analytic function in the neighborhood of t minus t naught, then we say that t equal to t naught is a regular singular point, and we want to find out the solution in the case of when t equal to t naught is a regular singular point. So, that we are going to do in this lecture here. So, here our aim is to find a class of singular differential equation which is more general than the Euler equation. So, one example of that t equal to 0 is a regular singular point for this Euler equation. If you look at t square d2y by dt square plus alpha t dy by dt plus beta y equal to 0. So, if you look at, then I can write this as that here your t equal to 0, at t equal to 0 this t square is vanishing. So, it is a singular point for this equation, and if you look at this alpha t divided by t square into t, here t naught is equal to 0. So, here t naught equal to 0, and if you look at, this is nothing but alpha, and if you look at t square beta upon t square, then it is a beta. So, we can say that alpha and beta are constant function, hence we can say that it is having a Taylor series suspension. So, it has only one component, that Taylor series suspension, and we can say that here t naught equal to 0 is a regular singular point for this Euler equation, Cauchy Euler equation, and here we have already solved this Cauchy Euler equation in a previous lecture. Now, we can simplify this equation number 1 in the following form. Here we simply divide it by t square. Here we are assuming that t is greater than 0 or t is less than 0, t is not equal to 0, we can say. Then here when we divide by t square, then it is d2y by dt square plus alpha by t dy by dt plus beta by t square y equal to 0. And here we can generalize this equation in the following form, that d2y by dt square plus pt dy by dt plus qt y equal to 0. Here pt and qt can be generalized form of alpha by t and beta by t square in a following way. So, here pt is written as p naught by t plus p1 plus p2 t plus p3 t square and so on. So, basically here we are adding a kind of power series in terms of t. And if you look at qt is q naught by t square. Now, we are adding terms q1 by t plus q2 plus q3 t plus q4 t square and so on. So, we can say that pt and qt has this kind of series suspension. So, the expression 3 is said to have a regular singular point at t equal to 0 if pt and qt have series suspension of the form 4 and 5. Equivalently, t equal to 0 is a regular singular point of 3 if the function tpt and t square qt are analytic at t equal to 0. So, here we can define this regular singular point in two ways, that either this pt and qt is having this kind of series suspension like 4 and 5, or you can say that tpt and t square qt are having Taylor series suspension at t equal to 0. So, both have equivalent meaning. So, equation 3 is said to have a regular singular point at t equal to t naught. So, this is what we have defined regular singular point of t equal to 0. Now, if we have a non-zero singular point, then in that case the function t minus t naught into pt and t minus t naught square qt must be analytic at t equal to t naught, or we can say that t minus t naught into pt has a Taylor series expansion in terms of t minus t naught, and t minus t naught square qt must have a Taylor series expansion around t minus t naught square, and a singular point of 3 which is not regular is called irregular. So, the meaning that these are analytic at t equal to t naught means here I can write t minus t naught pt as summation a k t minus t naught to power k, k is from 0 to infinity. Similarly, your t minus t naught whole square q t is equal to summation b k t minus t naught power k, k is equal to 0 to infinity. So, it means that t equal to t naught is said to be a regular singular point if it is a point of a singular point, and this t minus t naught pt and t minus t naught square qt must have this power series expansion in terms of t minus t naught, and we want to find out the solution in which case we have this kind of expression. So, now let us generalize the method used to find the general solution of the Euler-Cauchy equation to a more general singular differential equation of this form y double dash plus pt y dash plus qt y equal to 0, and here one or both of the coefficient function pt and qt is not analytic at t equal to t naught, means first thing is that t equal to t naught is not a regular point or not an ordinary point. So, we can say that here pt and qt is not analytic at t equal to t naught, and the ideas developed above suggest that we should try for a formal solution of this following form, which is known as Frobenius form. If you look at in this case in case of Cauchy-Euler equation, here we have taken pt as alpha by t and qt as beta by t square, and we got a solution of t to power r. Now, we are generalizing our pt and qt in way that pt is written as p naught by t plus p1 t p1 plus p2 t and so on. So, we are adding a kind of power series solution to our function pt and qt. So, we can say that here corresponding to solution, if we talk about, we must add some kind of t to power r is already a solution, then we can add t to power r plus 1, t to power r plus 2 and so on. These terms if we add in a solution, then we might have get a solution. So, keeping this an idea, we let us take solution as yt equal to t to power r summation n equal to 0 to infinity a n t n, and without loss of generality we are assuming that a naught is not equal to 0, because if a naught equal to 0, then it is what, then we can write t to power r, and now n is start from 1 to infinity a n t to power n, and we can write again it in a this form. So, it means that without loss of generality we are assuming that the first term of this series is basically non-zero, and here we are assuming that modulus of t is greater than 0. So, it means that here what we are assuming so far is that t equal to 0 is a regular singular point, and it means what, that t equal to 0 is a singular point. First of all, it must be a singular point, and second thing is that function tpt and t square qt are analytic function at t equal to t naught in a neighborhood of t equal to t naught, means what, that tpt have Taylor series expansion like n equal to 0 to infinity p n t to power n, and similarly t square qt is also having Taylor series expansion, that is n equal to 0 to infinity q n t to power n. To get a solution, we need to know possible values of r, for which we have a solution of our differential equation, and for which 7 is a solution, and then for each value of r. So, first we have to find out the values of r, for we have a solution, and then for each values of r we need to find out the coefficients, and it means what, that let us try for this solution yt equal to summation n equal to 0 to infinity a n t to power n plus r. So, first our attempt is to find out this r, for which it is a solution, and then we will try to get two kind of values R1 and R2, and corresponding to each R1 and R2 we try to find out the coefficient corresponding to R1 and coefficient corresponding to R2. So, so this we need to find out, and once we are able to find out the R1 and R2 and the corresponding coefficients, we can write down solution yt as summation n equal to 0 to infinity a n R1 t to the power n plus R1, and similarly the other solution. So, let us identify how to find out the coefficient these R1 and R2. So, for that let us assume that this is a solution. So, differentiate it. So, y dash t is equal to n equal to 0 to infinity n plus r a n t to the power n plus r minus 1, and differentiate again to get y double dash t, and it is equal to n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r minus 2. So, once we have y t, y dash t, y double dash t, we calculate p t y dash and q t y here. So, p t y dash is what? It is 1 upon t summation n equal to 0 to infinity p n t n. Here since we already know that t p t is having a series solution n equal to 0 to infinity p n t n. So, p t I can write 1 by t n equal to 0 to infinity p n t n, multiply by y dash t, that is n equal to 0 to infinity n plus r a n t to the power n plus r minus 1, and which we can write it here as t to the power r minus 2. Here we are taking r minus 1 out, and 1 by t is already there. So, it is t to the power r minus 2 into n equal to 0 to infinity p n t to the power n into n equal to 0 to infinity n plus r a n t n. Now, here we multiply to power series and to get the following form, that is n equal to 0 to infinity k equal to 0 to n r plus k a k p n minus k. Here how we multiply this power series? If you look at, if we have two power series like this, a k t to the power k into summation b k t to the power k, then we will have a series like c k t to the power k, where c k is given as summation n equal to 0 to k here, and a k and b k minus n here. Here I have just okay. So, here we have assumed like this. So, we are using this formula that c k must have, like if you look at a term here, then sum is going to be, sorry, here it is a n. So, it is a n b k minus n. If you look at the sum is going to be k minus n plus n is going to be k here. So, here c k must have this kind of form. So, using this formula, here we are writing that summation n equal to 0 to infinity p n t n into n equal to 0 to infinity n plus r a n t n. Now, I want a coefficient of t to the power n. So, it means that I am finding c n. So, c n is going to be what? Summation if k is from 0 to n here, and then here you find out, in this we find out p k, right. So, here we can say that this is b k and this is a k. So, here we can write that n here it is r plus k a k. So, this we are writing, and other one is n minus k. So, it is p n minus k. So, if you look at this k and n minus k is going to be, if you sum them, it is going to be n here. So, c n is going to be k equal to 0 to n. Here you can write b k and a n minus k. It is kind of symmetric thing. So, here it is your, I will write it, this is your a k and this is b k, if you write it like this. Then here we can write it, this product formula as n equal to 0 to infinity k equal to 0 to n r plus k a k. Please consider this as 1 n k and this as b n minus k. So, that is what how we write it, this product. So, p t y dash is written as t to the power r minus 2 summation n equal to 0 to infinity, and coefficient of t to the power n is given as k equal to 0 to n r plus k a k p n minus k t to the power n. Similarly, we can calculate q t y. So, q t y is 1 upon t square summation n equal to 0 to infinity q n t n into summation n equal to 0 to infinity a n t t to the power n plus r. Here again we apply the same formula. So, here this t to the power r we are taking out. So, we can write t to the power r minus 2 summation n equal to 0 to infinity, and here again we find out the coefficient of t to the power n. And how we can find out coefficient t to the power n? This is your a k and this is your b k. So, a k and b n minus k. So, b is what? q n here. So, q n minus k a k. So, k equal to 0 to n q n minus k a k. Now, we can simplify this further. We writing k equal to 0 to n minus 1. So, we are taking the term corresponding to n out. So, we can write q n minus k a k plus if you take k equal to n, then it is what? q 0 a n t n. We will understand how we are, why we are writing this. So, once we have this y dash t, y double dash t, calculate p t y dash and q t y, then we plug in all these value in your differential equation. So, here using the expression for y double dash, p t y dash and q t y in 6, we have the following differential equation by taking out the common factor t to the power minus 2. So, it means that here t to the power r minus 2 I am writing here. So, t to the power r minus 2 into this thing. So, here in bracket it is what? N equal to 0 to infinity n plus r minus 1 plus r plus n p naught plus q naught plus k equal to 0 to n minus 1 a k r plus k p n minus k plus q n minus k into t to the power n equal to 0. If you look at this, I can write it like this. So, here we have what? We have y double dash t plus p t y dash plus q t y equal to 0. So, y double dash t is what? Y t is our summation a n t to the power n plus r, n is from 0 to infinity. So, we can easily find out y dash t is equal to summation n plus r minus 1 a n t to the power n plus r minus 2, sorry, this is y double dash t. So, n equal to 0 to infinity. So, here we have just calculated the y double dash t, and p t y dash is basically what? P t is t to the power r minus 2 summation. Here we have calculated k plus r, a k and p n minus k, and it is what? Summation n is from 0 to infinity and it is k from 0 to n and here we have t to the power n. So, that is how we have calculated p t y dash. If you look at here we have calculated p t y dash is this t to the power r minus 2 n equal to 0 to infinity k equal to 0 to n r plus k a k p n minus k into t to the power n. That is what I am writing here, that n equal to 0 to infinity k equal to 0 to n k plus r a k p n minus k t to the power n. Similarly, we can calculate q t y. Q t y is again t to the power r minus 2 summation n equal to 0 to infinity summation k equal to 0 to n, and here we have b k and q n minus k and t to the power n here. So, when you plug in this value, then what you will get? Here we will get summation n plus r minus 1 a n t to the power n plus r minus 2, n is from 0 to infinity plus p t y dash is again, if you multiply t to the power minus 2 inside, you will get what? Summation n is equal to 0 to infinity summation k equal to 0 to n r plus k a k p n minus k t to the power n plus r minus 2. Similarly, you can write it summation t to the power r minus 2 n minus r minus 2. Okay. So, n plus r minus 2 into summation k equal to 0 to n b k, sorry, this is your b k q n minus k and t to the power, sorry, this is t not t to the power k, it is not it is we have already written t to the power n plus r minus 2 and it is equal to 0, it is equal to 0. So, here if you simplify this, then this is what we are getting here, that here, yeah. So, here we are getting this thing, that t to the power minus 2 if we take it out, so n equal to 0 to infinity n plus r minus 1 plus here corresponding to this we are taking the term here. If you put k equal to n value here, then I can write this k equal to 0 to n minus 1 plus the term corresponding to k equal to n. Similarly, here also corresponding to k equal to n we can take the term out. Is it okay? There is a small problem here. I think it is ak not bk, so it is ak here. So it is ak here. Similarly, here it is ak. Okay. So this is the correction here. So here we are writing this in term two term k equal to 0 to n minus 1 and k equal to term, n term. So and here also we are writing the same thing. So in this way we are getting the following formula: n equal to 0 to infinity n plus r minus 1 plus r plus n p naught plus q naught plus k equal to 0 to n minus 1 ak, and it is r plus k p n minus k because of p t y dash, and into plus ak into q n minus k because of q t y into t to the power n equal to 0. Now we can simplify it further. We can write n equal to 0 to infinity n plus r minus 1 a n t n plus k equal n equal to 0 to infinity k equal to 0 to n minus 1 r plus k a k p n minus k plus a n p naught r plus n. That is what we have written earlier, t to the power n plus k plus n equal to 0 to infinity k equal to 0 to n minus 1 a k q n minus k plus q naught a n. This is corresponding to k equal to n term t to the power n. That is this is the expression which we have simplified in this manner. Okay. So now since if you look at the left hand side and right hand side, and since in left hand side we have this expression and in right hand side we have 0, so it means that the corresponding term of t to power corresponding coefficient of t to the power n is going to be 0. So using this, equating the coefficient of t to the power n to 0, what we get: a n n plus r minus 1. So here if you look at here, we just calculate the coefficient of t to the power n here. So what you will get: n plus r minus 1 a n, and here coefficient of t to the power n is a n p naught r plus n. Here what you will get: q naught a n. So here we are writing a n into n plus r minus 1 plus r plus n p naught plus q naught plus. Now we look at this term here: k equal to 0 to n minus 1 r plus k a k p n minus k plus k equal to 0 to n minus 1 a k q n minus k, that we are writing here. So here we have writing a n n plus r minus 1 plus r plus n p naught plus q naught plus k equal to 0 to n minus 1 a k q n minus k plus r plus k p n minus k, that is equal to 0. So here we are trying to show that that equating the coefficient of t to the power n to 0, we get this following form: that a n into n plus r minus 1 plus r plus n p naught plus q naught plus k equal to 0 to n minus 1 a k q n minus k plus r plus k p n minus k equal to 0. And we can work it out here, and we can work it out like this, that here we have already calculated yt, pty dash, qty, and we have plugged in all these value, and we have this following thing: n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r minus 2, that is the expression for y double dash t that we have calculated here, plus expression for pty dash, that is n equal to 0 to infinity k equal to 0 to n r plus k a k p n minus k t to the power n plus r minus 2. So that is the expression for pty dash, and then we write down the coefficient expression for qty, that is t to the power n plus r minus 2 k equal to 0 to n a k q n minus k equal to 0. Now if you further simplify this, then here we have n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r minus 2. So this is nothing but y double dash t plus n equal to 0 to infinity. Now we simplify the coefficient of this t to the power n plus r minus 2 in pty dash as follows: you write k equal to 0 to n minus 1, and this is r plus k a k p n minus k, and the corresponding term k equal to 0 k equal to n we are writing here, that n plus r a n p naught, that we are taking out, plus n equal to 0 to infinity. Similarly we are doing for qty. So k equal to 0 to n minus 1 here, and ak qn minus k, and this is the term corresponding to k equal to n here. So this is for k equal to n, and here also it is k equal to n. Writing a n q naught into t to the power n plus r minus 2 equal to 0. Idea is to collect the term a n at one side and term which is less than a naught to a n minus 1 and other side. So if we simplify, then we are writing t to the power r minus 2 into n equal to 0 to infinity. Now collect the coefficient of a n t to the power n. If you look at what you will have, here we have n plus r minus 1, right, and here what you have, here we have n plus r p naught. So that is I am writing here, and here we have q naught. So here we are writing q naught a n t to the power n, plus now we are writing the remaining term, that is n equal to 0 to infinity, and term which are left here, that is k equal to 0 to n minus 1 r plus k a k p n minus k. Here we have this thing, and the term here, that is a k q n minus k t to the power n equal to 0. So now again simplifying this, t to the power r minus 2 summation n equal to 0 to infinity. Now n plus r minus 1 plus n plus r p naught plus q naught into a n, plus what we are doing, we are taking out this t to the power n term out, right, plus summation k equal to 0 to n minus 1 r plus k p n minus k plus q n minus k a k t to the power n. Here if you look at in this term, if you start from k to 0 to n minus 1, then here we are getting term from a naught to a n minus 1. So here we are just collecting the term coefficient of a n, and here it is the coefficient of a k, where k is from 0 to n minus 1. So this is the coefficient of t to the power n. So it means that coefficient of t to the power n has to be 0. So this quantity has to be 0 for each n. So here we say that equating the coefficient of t to the power n to 0, we get the following expression that we have just look at. Now we start from coefficient of t to the power 0, coefficient of t to the power 1, and so on. So if you look at the coefficient of t to the power 0 is going to be a naught r minus 1 plus r p naught plus q naught, that we can look at here in this way. Here if you look at coefficient of here, if you put n equal to 0, then you will get what, r into r minus 1, plus here we will get p naught r plus q naught here. So this is the coefficient of here a naught into r minus 1 plus r p naught plus q naught equal to 0. So here we will not get any contribution from this. So here we just using this expression for n equal to 0. So here we get a naught into this expression. Now if we call this as f of r, that is r, f of r is denoted as r into r minus 1 plus r p naught plus q naught, and this equation, this expression we call as indicial equation, same as in Euler-Cauchy equation. If you remember, in Euler-Cauchy equation we also have the similar form. So here f r represented by r into r minus 1 plus r p naught plus q naught. So if we take this expression as f r, then we can write down this as a naught into f r equal to 0. So here we have already assumed that this a naught is non-zero. So that coefficient of t to the power 0 has to be 0, provided that f of r has to 0. So that gives you the following thing. So now since a naught is non-zero, so 10 is true only when f of r equal to 0, that is r into r minus 1 plus r p naught plus q naught equal to 0. Now this is a quadratic equation in R, and will give two roots r1 and r2, and here we are just for sake of simplicity, we are assuming that whatever be the value of r1 and r2, we are assuming that r1 is the larger of these two roots. So r1 is greater than or equal to r2, that we are assuming here. So these roots called the exponents of the differential equation 6 at the regular singular point t equal to 0. So r1 and r2 are known as exponent of differential equation for at regular singular point t equal to 0 here, and so it means that that will give you exponents. Once we have exponent, then look at the coefficient of t to the power n and equate it to 0. So here we again use this thing a1 r plus 1. So, here what we are using, here we are using this expression again. So, here n equal to 1, if you put a1 into 1 plus r, here it is 1 plus r minus 1 plus 1 plus n p naught plus q naught, and here when you put n equal to 1, then you will get a term corresponding to k equal to 0. So, here you will get a naught q n plus p n. So, here we are getting this. So, we are using r. So, here we are using n equal to 1, and here you are using expression for n equal to. So, we are using 9 for n equal to 1. So, we are getting this equation a1 into r plus 1 into r plus r plus 1 p naught plus q naught plus a naught r p 1 plus q 1 equal to 0, and we already know that this a naught is non-zero. So, we can write a1, and if you use the expression for f of r, then this is nothing but written as f of r plus 1. So, we can write this equation as a1 into f r plus 1 plus a naught r p 1 plus q 1 equal to 0. So, once a naught is non-zero, you can calculate the value of a1 in the following way, provided that f of r plus 1 is non-zero. So, we can write in this way, we can look at the next coefficient of t to power 2 is 0, and we can write a2 r plus 2 r plus 1 plus r plus 2 p naught plus q naught plus a naught r p 2 plus q 2 plus a1 r plus 1 p 1 plus q 1 equal to 0. Here please note down, this is again this equation number 9 for n equal to 2. So, here we are looking at equation number 9, and we are for coefficient of t to power 0 put n equal to 0, and for coefficient of t to power 1 put n equal to 1, and coefficient of t square we are putting n equal to 2. So, we are looking at this equation number 9 again and again, and we are getting equation number 11, and similarly we can get this expression. So, this we can write in terms of f of r as a2 f of r plus 2 plus a naught r p 2 plus q 2 plus a 1 r plus 1 p 1 plus q 1. So, if we know the values of a naught a 1, we can get the value of a 2 from this. Similarly, equating the coefficient of t to power n is 0, we have this following expression a n r plus n minus 1 plus r plus n p naught plus q naught, and this is the expansion form of the formula this term. So, here we can expand in the following way. So, it is a naught q n plus r plus n p n plus a 1 and so on. So, that is equal to 0. So, idea is that using this equation number 9 and the fact that coefficient of t to power n is equal to 0, we are trying to find out the coefficient a naught, a 1, a 2 and so on, and provided that this can be possible, provided that f of r plus n is non-zero. So, here we can simplify in this way, that a n f of r plus n plus k equal to 0 to n minus 1 a k q n minus k plus r plus k p n minus k equal to 0. So, this equation 11, 12 indicate that the coefficient of a 1 is given in terms of a naught, a 2 is given in terms of a naught and a 1 and so on. So, the a n's are depending on r. If you look at here, here r is involved. So, we can say that a n's are depending on r, and the coefficient which we have already obtained, that is a naught a 1 up to a n minus 1, and this can be possible when this coefficient of a n is non-zero, provided that f of capital F of r plus n is non-zero for some positive n. In that case, we cannot utilize 12. If this f of r plus n is equal to 0, then I cannot utilize this equation number 12 to find out the value of a n. So, it means that here if r1 is equal to r2 plus n, here I am assuming that r1 is bigger than r2. So, if r1 is equal to r2 plus n for some integer which is n greater than or equal to 1, the choice r equal to r1 will give a formal solution. The choice corresponding to a bigger root will give you a formal solution, but choice corresponding to the smaller root does not give a solution. Why? Because when you apply r equal to r2, then f of r2 plus n is giving us f of r1 which is equal to 0. So, it means that corresponding to r equal to r2, you cannot find out a n using the formula number 12 because the a n into 0 is equal to something. So, we will see that under what condition this will also give a solution, that we are going to discuss this case. So, another case where we obtain only one formal solution of the Frobenius form is the case when R1 equal to R2. So, here you can find out the coefficient an using this formula equation number 12, provided that the f of r plus n is 0, and it is happening in what case? Here if r plus n is equal to 0. So, for so it means that here we are two values r1 and r2, and if r1 is equal to r2 plus n, it means that when you are looking a solution corresponding to r equal to r2, then when you put an, then an into f of r2 plus n is going to be f of r1, that is going to be 0, then this expression. So, if this expression is non-zero, you cannot find out a solution, but if this expression is 0, then we can look at some possible way to find out the solution here. Another instance where we may not get the other formal solution in the Frobenius series solution form is the case when both the roots are equal roots. So, it means that when r1 equal to r2, because I can have only one ans using this formula we can calculate, and we do not have any method to find out the other method to find out other formal solution. So, we will discuss these two cases in a separate way. So, in all other cases where r1 and r2 are real numbers, the above presented procedure give two independent real solution of 6. And consequently, if fr equal to 0 has two real roots r1 and r2, when r1 is greater than r2 and they do not differ by an integer, it means that your r1 is bigger than r2, but r1 is not equal to r2 plus some n, where n is some integer. In this case, we have two linearly independent solution, and corresponding to r1 and r2, we can have a solution like this: y t equal to t to power r1 summation n equal to 0 to infinity a n r1 t to power n, and corresponding to r2 we have y to t, that is t to power r2 from n equal to 0 to infinity a n r2 t to power n. And these solutions have radius of convergence r minimum of r1 and r2, where r1 and r2 represent the radius of convergence for TPT and T square QT, because TPT and T square QT are having power series expansion. So, it must have a radius of convergence. So, if you take the minimum, then that is going to be the radius of convergence of the solution here, that is the guarantee of this method. We are not going to prove the following statement, but you take this as a given thing. If we f of r equal to 0 has two roots r1 and r2, and these are different and they are not different by an integer, in that case we have two Frobenius series solution given in the following form: y1 t equal to t to power r1 n equal to 0 to infinity a n r1 t n, and y2 t equal to t to power r2 n equal to 0 to infinity a n r2 t n. And this procedure gives you that this series solution is valid in a region having radius of convergence r minimum of r1 and r2, where r1 and r2 are radius of convergence of TPT and T square QT respectively. So, in this case we have two Frobenius series solution method guaranteed. So, here I will finish, we will continue this in next class. Thank you very much.